Hey everybody, Mr. Judson here. So today we've got a short lesson. We're actually going back to good old pre-calc days and doing some exponential growth or decay problems. And they kind of tie in with our solving differential equations and kind of the main thing we really need to get to. So this will be more of a review day. So here's our first problem. It says that carbon-14 has a half-life of 5,715 years. And the question here is, how old is a sample with 21% of its carbon-14 remaining? Carbon-14. And so if you remember this really has to do with our PERT formula. A equals P times E raised to the RT. And remember, we use this formula anytime something changes continuously. Well, if I've got some carbon-14 that's sitting in the ground and it's rotting and decaying, that's a continuous process, right? And so we want to use this formula. P again is our original amount that we start with. A is the ending amount. We know E is the number 2.718. R is the rate at which it's decaying. And T is the time it takes to get from our initial amount to our ending amount. And so what we want to do is think of this as two separate problems. First, I have to figure out the rate at which carbon-14 is decaying. And so when it says a half-life, that means whatever I start with, I'll have half of that remaining later on. You can pick whatever number you want to start with. You want to start with 100 grams, you'll have 50. You want to start with 10, you'll have 5 grams. You want to start with 1, you'll have 0.5 grams. And so pick whichever number makes the most sense. I think 1 and 0.5 make the most sense. So I'm going to say 0.5 equals 1 times E raised to the R. That's what we're trying to find right now, is the rate at which this carbon-14 is decaying. And we know it took 5,715 years for that to happen. And so what I need to do is just solve this equation for R. I'll go ahead and get rid of the 1. So I've got 0.5 equals E raised to the 5715R. And we know that when you solve for a variable that's in the exponent, you have to use logs. And if you remember last year, I told you, let's just always use natural log, because sometimes it's important and sometimes it's not. But if it's important sometimes, why not always use that? So once I do that, that allows me to bring the exponent down in front. So I have natural log of 0.5 equals 5,715R times natural log of E. And that's why we wanted to use the natural log, is because natural log of E is equal to 1. And so now my equation is going to be this. Natural log of 0.5 equals 5,715R. I'll move this number over and divide. All right, so if I do that on the calculator, I've got the natural log, which is right here where your x variable's at, of 0.5 divided by 7,515. And so what I got was an answer that's in scientific notation. That E negative 4 means we've got to move the decimal point 4 places in the negative direction. So what I got here is that R equals, I've got 1.219, and I've got to move this decimal point back this way 4 places. So let me erase that. There's 1, 2, 3, 4, and it was a negative number. So that is our rate of decay of carbon-14, which we knew it's a very slow rate, so I'm not surprised that we got that number. All right, so now the question is, how old is a sample with 21% of its original carbon-14 remaining? So that means I started with 100%, which as a number that's 1. I now have 0.21 remaining. I've got e raised to the negative 0.001222, I'll just call it that, times t. And so now I just have to solve that, and I'll do it the same way I did the first part of the problem. I don't really need the 1 there, so we'll get rid of that. Take the natural log of both sides, so natural log of 0.21 equals natural log of e raised to the negative 0.000122t. I'm still going to keep track of that exact number in my calculator. So now I bring that down in front, and I've got natural log of 0.21 equals a negative 0.000122t times the natural log of e, which is just 1. I won't write that down. So now I just got to move this number over and divide. And so I've got natural log of 0.21 divided by, I'm going to use last answer, and what I got was an answer of t equals 12,867.544 years. That's how old that sample is. Okay, let me give you guys one to try. All right, so here's a similar problem for you guys to try. As opposed to something decaying in the ground, we now have a population which is growing, which is also a continuous thing. So we're still using the PERT formula. And it says here that Fircrest had a population of 6,200 people in 1995 and 6,735 in the year 2005. What is the population today in the year 2020? So this is just like the other one. We have to do it in 2 stages. We got to first of all figure out what the growth rate is for the city, and then make our prediction of how many people in 2020. You guys go ahead and give that a shot. All right, so first I'm going to figure out the growth rate. Still using the PERT formula. We had 6,200 people originally. Population grew to 6,735, and it took from 1995 to 2005, it's 10 years for that to happen. So R times 10. All right, so first thing I'll do is I'll move that 6,200 over and divide. All right, so I got 1.086 equals e to the 10r. Now I'll take the natural log of both sides. So the natural log of 1.086 is going to equal, when I take the natural log of this, I'll bring that 10r down in front. I'll still have times natural log of e, but that's just 1. And so now I just have to divide by 10. So natural log of that number divided by 10, and I get r equals 0.0083. That's not my final answer, so I'm not really worried if it's rounded to 3 or 4 or whatever number of digits. I'm still going to try and use the exact value in the calculator. But that's the growth rate of Fircrest. It's got less than 1% growth rate. So now we want to know what's the population in 2020. That's going to be the ending amount. I started with 6,200 in 1995. I've got e raised to the 0.0083. And I guess I know the number of years from 1995 to 2020, that would be 25 years. So I don't really have to solve this time. I just need to plug all that into the calculator and see what I get. So I've got 6,200 times E raised to this last answer that I have times 25. And what I got is 7,625.29. I don't think we want 0.29 of a person running around, so we should round this to the nearest whole number. Since it's less than 5, we just keep it right there where it's at. All right, there it is. That's it. Short day for today. It's just review on solving exponential growth functions. And so the problems you guys will see would be similar to this. All right, so here's our assignment for tonight. It's number C8, page 419. We're going to do 37, 39, 42, and 62. And I'm almost done with my Central Washington information. I've been saying this all along, things change almost daily, and sure enough, they do. So I just need to revise a few things, and then I'll get that information out to you guys. All right, you guys take care, have a good day, and stay safe.